session will be about an interesting topic in machine learning. As you know, data science is a science that exists for a while. It's not new. But the excitement that happens in data science happened to the recent development in machine learning. Companies like Google, Microsoft, they put a lot of effort in their research and development, and they developed more and more frameworks for us to use. At the same time, universities also provided some contribution, or a lot of contribution to data science. One of the key frameworks that has been developed by Google, for example, it is TensorFlow. TensorFlow was developed a while ago by Google for their internal use. And recently in 2015, they decided to make it open source to share it with the public. And what's powerful about this TensorFlow, it's very good when it comes, it really shine when it comes to deep learning. Today's topic will be about using image classification in TensorFlow. So let me welcome Zaid Alyafeai, who will present with us how to use TensorFlow in image classification. So please welcome with me Zaid Alyafeai.
Good evening. My name is Zaid Alyafeai. I am a master's student at King Fahd University. I'm studying computer science, especially interested in machine learning. So my specialty is about computer vision, especially using it in medical imaging. So today I'm going to talk about how to use machine learning in the browser. So sometimes you are interested in making a prototype, for instance, or something that you made in machine learning, something that is smart, and you want people to try it. So the easiest way is to train the model, then just deploy it for people to use it easily. So let me first start by introducing neural networks. So neural networks offer us the ability to learn from data. They are like graph structures that contain nodes that are called neurons. The connections carry what we call weights. So there is something interesting, which is a demo that is offered in TensorFlow. I will share it with you. And it runs in the browser. So here it is. So this is the structure of a neural network. As you see here, you can see the inputs here, x1 and x2. You can think of the input as x and y coordinates in the system. And this is a neural network. So here we see the neurons here. There are 4 neurons here in this layer. We call this a layer, which is a collection of neurons. And this is the output layer, which contains 2 neurons. So the basic idea behind this is that we are trying to classify inputs. So here we have some inputs here. If you see this, we have some inputs in the XY coordinates. They are labeled by X and Y. Each point in the coordinates contains a color. The color represents a label. So we have the orange label and the blue label. So the basic idea is that we want to try to learn from this data such that if we are given a new point, we will try to give it a class or a label. So if you try, for instance, this one, so these are the points in the plane. So we'll try to find some kind of classification methods such that we separate between these 2 classes. There are a couple of things that I need to introduce for you. For instance, here is the learning rate. The learning rate defines how fast the model is learning. You don't want the learning rate to go too fast because it will diverge. And if you put it too slow, the model will learn very slowly. We have also what we call the activation function. The activation function is a kind of function that's applied to the output of each neuron. So here we have some activation functions. There are some non-linearities. They define a non-linearity to the model. Here you can also define the type of problem that you are solving. You can choose either classification or regression. So for instance, if we have this model and we start training, we will see that there is what we call epoch. The epoch defines how many times we apply the input or the training data that we have to the neural network. So at each epoch, we input the data once. So if we try training for some time, so we see that the model is training by putting a separation plane between the blue class and the orange class. So here you see what we call the training loss. The training loss defines how the model is doing for the training data. And the test loss is defining how is the model doing for the testing, for the test data. So the test data is not seen by the model. We only input at each time the training data. So you want this number to go as low as possible. If it's low, then you know that the model is training. You can also try different type of data. So this data is not linear. If we try to, for instance, learn, so it gives like a live explanation of what's happening. You can also increase the number of layers we have here. For instance, here we have 2 layers. If we try the same method, for instance, for this one, so we will see that the model is not learning well. This is because there is some kind of non-linearity in the model, such that it's not captured by the model we are designing. If we try to encapsulate this type of non-linearity, we need to add more features. So the feature defines some kind of encoded information about the input data that we have. The more features that we have, the better the model is learning. For instance, here we can add some sinusoidal data, and we try learning. So here you can see that the model is learning well by encapsulating more features to the model. So it separates between the orange class and the blue class. If you hover over these connections, you see what's called weights. So the weights are some kind of learnable parameters. This is what the model is try to tune such that the model loss will become as low as possible. This is done through a method called backpropagation. We will not go over the theory of this stuff, but you just give. I try to give you some overview of what's going on. So, do you have any questions about this? Do you have any questions about the variables that we have here? Any concerns about this? Yeah, this is designed in TensorFlow, but it was deployed in the browser, so everyone can try it. The problem with TensorFlow is that you cannot easily deploy it for people to try it. You have to have you have to set up a GPU, you have to set up the library, but anyone, you can start your phone and try this on the fly. Yeah, directly in the browser. So yeah, so this is what I'm trying to illustrate today, that you can design some models such as people can try it from home, so they can learn better this way. So I'm going to give an overview of TensorFlow. So TensorFlow is an open source machine learning library that was announced in 2015. It was before that internally used in Google, but after that it was open source for people to collaborate and participate in the development of TensorFlow. By the way, anybody can change the code and send it to Google, and they will update their database. So it's kind of a community collaboration. So it offers APIs for beginners, experts to develop desktop, mobile, web, and cloud applications. So it's easy for deployment for computation across a variety of platforms, such as CPUs, GPUs, and TPUs. So we all know the CPUs. GPUs are the graphic processing unit that is used for basically, it was used for gaming purposes before, but nowadays it's mostly for deep learning, because when you are doing some computation on models, you are doing lots of computations that are happening at the same time. So GPUs help you in making this faster, because CPUs are not optimized for this process. TPUs are fairly new, and they were designed by Google. It's called Tensor Processing Units. They are optimized to be used only for TensorFlow. So this is the overall structure of TensorFlow. So it contains high-level APIs, mid-level APIs, low-level APIs, and the kernel that is running on. So TensorFlow was designed using C++. After that, it was ported to Python because it's the most used language across data scientists. It contains many other platforms. So in the mid-level API, you can design layers, you can manipulate datasets, you can create different metrics to know how the model is doing. And we have also estimators, which is to design high-level APIs. So this is a basic code for creating a neural network in TensorFlow. So first we import TensorFlow. Then we created two layers. These are the same, kind of the same layers as we saw in the demo. So the first layer contains 512 neurons, and the second layer contains 10 neurons. In between these layers, there are some what we call activation functions. They are used to learn complicated information in the data. After that, we can compile the model. So there are some vocab here. For instance, an optimizer. An optimizer is something that updates the model. So when you are learning the parameters of the model, which are called the weights, you need to specify some kind of update role. So this is an algorithm that's ready for people to use. This is the safest algorithm to use. So if you don't know how to set up your model, just use Adam. The loss calculates how good your model is learning. So there are a couple of loss functions. Categorical cross entropy calculates loss for classification problems. The last one is the metrics, which calculates the accuracy of your model. So, for instance, how accurate your model is doing. It gives you a percentage. For instance, if your percentage is high, 98%, that means you are doing well and you are classifying the data that you are doing correctly. Okay. Yeah. Oh, okay. So yeah, so the question is whether Keras is related to TensorFlow. So Keras was designed independently of TensorFlow. So it's a higher level API. TensorFlow is kind of lower level API. It does not provide you with all, at least in the past, it was not providing all the high level layers, for instance, the models. You cannot create a model. But Keras here was designed independently of TensorFlow. Then it was recently added to TensorFlow to make the operation of creating models much more easier. So here, if you compare between how it was designed before and how is it designed now, it's completely different. You would need like many more lines of code to create this in core TensorFlow. But with the application of Keras, it becomes much more compact and readable for people. So what is TensorFlow.js? So this is like a part of TensorFlow that was designed to run using JavaScript. So many people, many developers around the world, they are using JavaScript, especially to design models to run in the browser. So this was lately or recently developed only this year in March. So it's completely new. So what does TensorFlow.js allow you? So it allows you to develop ML or machine learning with JavaScript, so you can train directly in the browser. Also, what's really nice is that you can run existing models. So suppose that you have a deep learning model that already used to classify, for instance, between dogs and cats, and you want people to try it. So you just convert it using TensorFlow.js and run it in the browser. So anyone in the world can try it directly from the browser. So here is the basic structure of TensorFlow.js. So there are what we call layers API and operation APIs. So the layers API is just like Keras. You can create layers, you can compile the model. The operation APIs allows you to do operations like multiplication, addition, subtraction. And directly you can run this in the browser, and it will use WebGL to run this in GPU. So for instance, this is like a Keras model. So I want to show you some demo. So this is the demo that I created. I'm not sure why it's showing like this. So for instance, you can, so the basic idea of this demo is to be able to draw stuff and it will directly tell you what it is. For instance, I can draw a t-shirt. I'm not sure about my drawing. So this is classified as t-shirt with 100% accuracy. You can, for instance, create like something. So this is classified as mountain with 97%. Let us create some stuff. So this is like a face, smiley face. The task create, for instance, something didn't work correctly. So it was clocked with 9%. So this is something that runs directly in the browser. So anybody here can try it directly now. So now I'm going to show you how to do this super easy and to train it. Yeah. Yeah, I'm going to explain all of this. So this is the main demo of. So I'm going to do to explain how to do this from scratch, from collecting the data sets to deploying this in the browser. So can you give me something to draw? Car. I'm not sure if it is inside the dataset, but I will try. Yeah, car. Yeah, you can. So let me try something. It's a butterfly. Mobile phone. It's a cookie. uh, we can stay here all day trying. So this is eyeglasses. You can draw, for instance, a tree. It's a table. So it doesn't work all the time, but you get the idea. Okay. So yeah. So I'm going to explain how things work here. So let me close this. Um, So I'm going to explain the pipeline of doing something similar. So first of all, you want to collect the dataset. You want to think of a suitable dataset. So this is just a general pipeline. Then I will explain details how to do this for this demo. So first, you need to collect the dataset. This might be difficult, especially if the dataset is not available. So you have to collect it yourself. After that, you need to pre-process the data. Basically, the data that you can find is unconstrained. It might, like, every image might be of different shape, of different size. You need something that is able, such that you are able to input it in your model. After that, you need to create a model. Then you train it for some epochs. And so this is the basic pipeline of doing something similar. So this is the dataset that I trained on. So this dataset was collected by Google. So it contains around or more than 1 billion images that was drawn by people. It contains more than 300 classes. So for instance, this is a cookie, this is a dog, this is an envelope. So for each class of these, we give a label. For instance, this we give it 0, 1, 2, 3, 4. Yeah. So as long as you have the dataset that you are training on, things are much easier. What if you don't have this? What will you try? Do you have any suggestions? Yeah. Yeah, so you can ask people to do that. Actually, there is big companies use what we call mechanical Turk. So they ask people to do stuff for some kind of for like $1 per image, for instance. Uh, so yeah, yeah, you can figure something similar. The nice thing about this data set, it was collected from all over the world. So lots of people participated in creating this data set, and it's really big. So how to train on something similar? What you need to do is to create what we call a convolutional neural networks. So this is different than a neural network. A convolutional neural network work on images. So the input is an image here, and the output is a class. So for instance, you input like the image of a cookie, and it will output to you like this has class 1, for instance. So a convolutional neural network contains many layers as much as you can. Basically, the most important layers are called convolutional layers and pooling layers. So what's the convolutional layer? So a convolutional layer applies some kind of filters into the image, and it scans the whole image by doing some operations between these filters and the image. These filters represent at first some random data, and with time these filters will try to, like, for instance, know what type of local data we have here. For instance, this filter might be able to know that there is an edge there. With time, and as you go deeper in the convolution layer, later layers will learn some complicated structures. At first, it will learn, for instance, edges. Then it will learn, for instance, circles, triangles, and at the end, it will give a good classification information about the data that you have. The problem with this is that this operation is really expensive, and you need to reduce it as you go deeper in the network. To do that, we do what we call a pooling layer. So a pooling layer will reduce the spatial size of the image. For instance, here we have a 6x6 image, and it will reduce it to a 2x2 image. So there is what we call a max pooling. It will take the max number that you have in each operation. For instance, the maximum number in this window is 5. So these are basically the most important layers. There are many other layers, but I don't want to go into details of this. So we will start training. To do that, we will use Google Collaboratory. So Google Collaboratory allows you to do training on free GPUs directly from the browser. So I already prepared a document. I'm going to go over all the steps. So this is the Google Collaboratory. It's some kind of a notebook if you are familiar with the Jupyter notebooks. So if you go into notebook settings here, you will see that you can choose either none, which is a CPU, GPU, or a TPU. Yeah, so it offers around 8 GB of memory for anyone to try it. So the first thing to do is to click connect. So we will run our notebook. So it will initialize. It will initialize the kernel. So first of all, we will download the dataset. So for simplicity and for the sake of this presentation, I am going only to download the dataset for only 10 classes. The model that I showed you earlier was trained on 100 classes. So I chose some classes. So here I'm creating a folder called data. So it will create the folder. What? Again? Yeah, no, this is like it collects some like 15 gigabyte of drive space for you temporarily. Okay, you can also mount your drive directly to here, and you can, for instance, upload the images or the training data to the drive, then train directly from here. So you will increase your, for instance, if 15 gigabyte of free space in drive, you can. So here we will. The nice thing is that this dataset is really big. So these 10 classes contain like 1.5 gigabyte of memory or of hard drive. So if you want to appreciate really quick internet speed, you can see that it's very, very fast. So this is 1.5 gigabyte of memory. It will download it really fast because this is happening in the cloud. So you are not down. No, this is only 10. I'm not sure, but you can imagine that this is 10 classes and the whole size of this is 1.5 gigabyte yeah, gigabytes. So if you multiply it by 100, then multiply it, if it contains like 300 classes, yeah, 300 gigabytes. Here we do some imports. So we import TensorFlow, Keras, and some helper libraries. So the first thing to do is to load the data to a variable in Python. So this is doing this work. So at each time we load this data into some variable. So these data are like the extension of it is an NumPy array. An NumPy is a library in Python that allows easy manipulation of arrays. So it's like, in order to load it, just click MP to load the file. It will load it directly. So after that, we do a randomization of the dataset, because if you don't randomize the dataset, the model will learn by order. So it will learn, for instance, this is like class 0, then class 1. We don't want something like this. We have to randomize the dataset. Then after that, we separate the dataset into training and testing. So for training, we want the model to see this data. So we train. And after we finish all the training, we need to see how is the model doing. So the test data is not shown to the model, only at test time. So we load these the images to these variables. So here we have X-train, which is the images to train on. We have the Y-train, which is the labels that we have. For instance, for each data here, we have a corresponding label. So here we are printing the size of the training set. So here we have around 30,000 images for training and 8,000 images for testing. So the question is whether we should check if the classes are balanced across the training and testing. if you randomize the dataset, you don't need to do this. So the data is random and it's huge. So also the number of classes are the same in the original dataset before we separated it into training and testing. So in terms of this, you might think that we need to do this, but if the dataset is huge, you don't need to do this. But if you have like images, if you have less than 1,000 images, you need to make sure that the labels are balanced. So here we can show some images across with the class name. For instance, here we will, so this is a laptop. The images are 28 by 28, so they are really, really small. This is for the sake of training a very small model. But if you have, like, sometimes you will input some 200 by 200 images, so your model will be much more bigger than this. So this will pick up a random image and it will show its label. So this is a LiDAR. This is a camera. This is pants. So here we show how is the shape of our training set. So here we have 30,000 images in this shape. So each image, you can think of it as an array of pixels, which is with the length of each image 784. After that, we need to pre-process the dataset. So convolutional neural networks accept images with certain size. So you need, like, for instance, if the image is gray, which is what we have here, you need the image to have, like, for instance, the size or the shape of the image. For instance, here it is 28 by 28. So the image size is 28 by 28. So here we reshape the image into this size. Then we normalize the dataset. This is very important because neural networks they don't work perfectly if the dataset is not normalized. So here for each pixel we divide it by 255. So we know that in computer science images are represented for each pixel. It has the value from 0 to 255. Okay, so here when we divide it by this number, it will be between 0 and 1. So after 28 by 28. So from this, I will show you now the shape. So this is now the shape. So it becomes an image. The first number here represents the width, and this one represents the height, and this one represents the number of channels. Because we have gray images, the number of channels is only 1. If you have colored images, the number of channels is 3.
Since we have gray images, why do we need to have that one? Couldn't we just use 3 dimensions and could be simpler?
Yeah, but you need your library that you are using. So the question was, do we need a 1 here? We just remove it. Yes, you can do that. But normally, neural networks or libraries accept 3 dimensions. So this is just a naive way of applying this. It's not representative of the data, but you need to do this because TensorFlow accepts 3 dimensions.
Yeah, I mean, if it's not generalized, yeah.
Yeah.
It's generalized, but wouldn't it be better performance?
No, it doesn't affect. You have to have this dimension because you have to create and neural network, and these layers only accept 3 dimensions. Okay.
Can you go up in your code here? You divided by 255.
Yeah. Oh, okay. I didn't explain this. So here normally each image is represented by a number. For instance, a 0, a 1. For instance, a car is a 1, a cookie is a 0. Here we need to do what we call one hot encoding. What does this is just kind of converting each label into I will show you what's here. So here, if you see the training data, yeah. So for instance, this is 4, but it is converted into this format because in training we need to have it in this format for the neural network to work. So this is kind of some extra stuff that we have to do because convolutional neural network for classification need to have an output in a categorical format. So here is the model that we have. So here we call what we sequential model. So we will add different layers. First we add a convolutional layer, then a pooling layer, a convolutional layer, a pooling layer. So we have 3 pairs of convolutional layers, followed by pooling layers.
Is this something that you came up with, or you got some from somewhere?
Yeah. So the question is, do you take this architecture from somewhere else? This is like the initial setup for convolutional neural networks that started in 2012. This is called an AlexNet. So this is the most basic one. Now neural networks are much more complicated than this. But since our data set is basically really simple, we don't need something complicated. But you can, for instance, you can change some stuff here and have a better performance, but it will not be that huge. You need to completely change the architecture in order to boost the performance. So here you will see some stuff here. For instance, here 16, 32, 64. These are the number of filters that you have in each layers. So these filters learn some structure about the dataset. For instance, some filters will learn that if you have a car, you need to have some kind of circles for the tires. These filters will learn, for instance, some edges, horizontal edges, vertical edges. At the end, we change the shape of our model. Here is a summary of our model. So here it shows you how is the model done. For instance, here the input shape is for instance here it is 28 by 28 by 1. This one. Then we have a convolutional layer that will be inputted here, and it will have this shape. Then the output shape will be decreased as we go down, and at the end we will have 10. 10 represents the probability distribution of the data. For instance, this 10 will contain an array with probability for each class. For instance, it will show you that this is a tree with probability 0.5. This is a car with probability 0.3. So for each image that we input, we will have an output of shape 10. Here we can do, finally we can do the training. So I need to run this first. So in the training, at each time we take some batch of the data and we input it to the model and we tune the parameters. We see that the accuracy is increasing as we are training. This is for the training set, and this is for a validation set. The validation set is some part of the training set. So Keras divides this randomly into training and validation. This is the accuracy for the testing set. So we got some good accuracy, around 99%. So it only misclassifies images by 1% of error. So now we can do some inference. Yeah. So the metrics that I used, it's not accuracy. So here I am saying that the class is correct if one of the 5 top classes exists. For instance, you draw a car. If the car exists within the top 5 predictions, you will say this is correct. Let us try. Why not? It will be much less, of course. For the sake of experiments, we'll see what's the accuracy. So yeah, we see that the accuracy is 94, which is not that bad. Yeah. But actually, because in our demo we show 5 classes, so yeah. Here we show the inference. So for each image we show the top 5 classes that was predicted. For instance, here for this image, we have the top. The first prediction is laptop, then table, then ladder, then camera, then pants. This is incorrectly classified as table, but the second prediction is eyeglasses, which is what is the correct class for this. So now we have our model, which is this variable. After that, we can, first of all, do you have any questions about what we have so? What do you mean? So the question was, yeah, so you need like high throw positives, for instance. You need actually to try different models and compare between them, which one gives you the best results. But generally, you cannot say that this model is 100% because there is no model that, unless it's overfitted to the training data that you have. So here what we are doing is we are installing TensorFlow.js. This is a library that converts the model that you have to run directly in the browser. So we are waiting for it to install. So everything is happening in cloud. I'm not installing anything to my system, so you don't worry about if this is happening in your system or not. Yeah, so you can also use it to train in the browser. Yeah, okay. Yeah, I need. No, it's not. It's not. This is not installed here. Yeah, in Collab. Yeah. So this library is not existent there. I have to install first. So first I have to save the model in this format. Then I just convert it. So now this model is in a web-friendly format. You can load it to any HTML file. So this is the structure that we have. Yeah, so this is the structure we have. We have two files. We have model.json, which contains the architecture of our model. And this one contains the weights or the learnable parameters that we have. Now, in this format, you can load it to any browser directly. Just I will explain it now. So actually here you can compress the file and download it directly to your system. Yeah, so no, you don't need it. Just I will show you now how to do it. Yeah, JSON file, you can load it directly. So we had two files, JSON file and another weight file. So first, you need to have this script in your HTML file. You can copy it from the page directly from their page. After that, just add this code. So you load the model and you wait for it to load. This is it. You don't need to install anything. Just import this script and load. Yeah. So yeah, it depends on the. So the question was, what is the size of the model? This actually is very critical because browsers are slow compared to running it in your local machine. So it might be very slow. So you need your model to be as small as possible. So I'm not sure about the size of the model that we created, but usually you need something less than 20 megabytes, and it's usually is. I will show you some demos of cool things that you can create. So after you load the model, you need to. So when you are drawing on the canvas, you need to convert the image that you have into something that you can input to your model. So for each image, we convert it into shape 28 by 28, and we do the same normalization that we did. So we divide by 255. That's it.
Drawing component, is it something part of TensorFlow or you just...
No. So the question was, is the drawing part of TensorFlow? No. Just this is another library. It's called Fabric.js. Each time you draw something, it will give you the image. After that, you need to do some post-processing. So, for instance, you need to find the top classes that you predicted, and you need to have the class names. So this is the basic structure. You need to do preprocessing for the image data, then you predict, then you do some post-processing. So yeah, but in JavaScript, you need like to extract the top classes. For instance, it will give you 10 classes. You need to show to the user that this is the predicted class. So you need to do some post-processing, right? So I will show you some cool stuff that I did with TensorFlow.js. So here is my page first. Yeah. Yep. So so this code converts drawings into images. This is, yeah. So this is completely different. This is a more complicated approach. It's used some model. It's called Pix2Pix. If you want to read about it, here is all the information. We have the code and the demo. I'll try it later. This is me, by the way. So this is a real-time segmentation. So it recognizes my nose, my hair, my mouth. What? Yeah, so the question is, do we use semantic segmentation? Yeah, so this is kind of semantic segmentation. So the data set, for each image, we will have a class per pixel. So this pixel contains class yellow, which means that it's here. So here also I have image reconstruction. So it tries to reconstruct an image out of this. This is the demo I showed you earlier. So this is a cup. Also, I made some demo for Lattic. If you know Lattic, you create a symbol and it will show you the Lattic code for it. Also, there is a demo for style transfer. So given an image, I make some style. So it's like Photoshop. You input an image and it will show you a style on the image. So this is converted. So this is a completely generated image. It's not there. You just apply some class from here. Here, it's all explained here. So this is the model. This is the paper that implemented the model. You can read everything here. So I will make these slides available. So if you want to read more about it. So this is like, yeah, this is real-time style transfer. So it takes my image and it makes some transfer, some stylization to it. So yeah, so the code is on GitHub. Yeah, you can try it. Yeah, no, I'm not running it right now, by the way. This is just video, but I will run a demo for you right now. Because the model takes some time to download, so I will show you from my local machine. So for instance, yeah, so yeah, so here you can create, for instance, this is live, so you are running it really now. So for instance, let me change this. For instance, this is the face. You draw a face. This is not a face, by the way. So you have a hair. Not sure if this is a hair. You make some, for instance, the eyes. So with time, it starts to recognize that this is a person, a really strange person. There's some tools. You can add ears. So no. So these are the only classes. Yeah. So also we have some cats. So here we are loading the model. Here you can draw directly. For instance. So this is a cat, maybe. So you can do lots of cool stuff. For instance, here, you can paint some stuff. For instance, this one, you paint some classes, water, grass, tree. So I will not take a lot of time. If you need to read more about this, I made some tutorials. This tutorial is an introduction to TensorFlow.js if you want to go deep in it. Sorry. So it's published in Medium. You can read everything about it from scratch. Also, there is another tutorial about how to train a model in Colab, then run it directly in TensorFlow.js, like the one I explained here. Also, there is a cool website that shows the applications of using TensorFlow.js on different projects from the community. So all of these you can try all of them. So basically, what's nice about machine learning is that all of these things are really, really new. So people did not have even the time to try and make this commercial, because it's really, everything is happening really quick. So TensorFlow.js was introduced just around 6 months ago. So yeah, there are some attempts to incorporate some stuff like this in Photoshop. So yeah, so this is like cool stuff. So yeah, for instance here, this is some cool demo that was not produced by me, by some people. So here, the model might not load really fast. So yeah, so what this is doing is that you just draw a stroke and it will combine it into some class that you choose. For instance, here it will try to draw a bird out of it. This is completely done or generated using a neural network. So it's trying to draw a bird out of the stroke that I made. You can, for instance, choose anything you want. An ambulance. I will wait for it to load. So I'm not sure what's doing here. So this is completely generated from a neural network. So this concludes my presentation. If you have any questions.
Is there any other libraries than TensorFlow that does something in the browser?
So the question was, were there any libraries that do the same thing? So yeah, but it was completely restricted in terms of applications. So TensorFlow.js opens the world for JavaScript developers to create something really useful. It's not something restricted. It provides lots of tools in order to make your application really cool. So I think we are done, right? So if you have any questions.
Question about Colab.
Yeah, okay.
Does it allow you to run long training sessions? I mean, for instance, for image training, you might need hours or
Yeah, okay.
days in some cases. Does it allow you to do that?
Yeah, so the question was, what's the maximum time you can have on Collab? Actually, the maximum time is 12 hours only to use the. Sometimes it interrupts randomly between them, but the basic idea is that you can save the model. So at each time of training, you are saving the model into your drive, for instance, and you can continue training later. So this is for free, and you want to make use of it. So they don't allow you to train for more than 12 continuous hours. Yeah. Actually, to go around this, sometimes I have like different accounts, Google accounts, and when I finish my time there, I I go, don't tell anybody. Okay. Uh, yeah. So in terms of TensorFlow, the best I prefer for me, I prefer that you search for some collab notebooks. So I will show you something here. So here is what we is called seed bank. So this seed bank, it was created by Google. So you have different type of class of problems in machine learning. You have classification, unsupervised learning, recurrent neural networks. And what's nice about this is that you can open this directly in Colab, and it's kind of a tutorial that you can't learn by coding. So you run it directly in Colab, and you can see what's happening by coding. So this is the best way I think of trying things. It's better just it's better not to just read stuff. So you want to try the code and what's happening there. So for instance, this is an example. So it's a tutorial, and at the same time you are learning what's happening there. So it contains many models. So the main pain in machine learning is data sets. Yeah, so you need to do, uh, data sets. There was a new website offered by Google for searching for data sets. So this is was introduced, I think, only 1 month ago. So Google dataset search, you can search for anything. Yeah, ImageNet. You can use ImageNet, but sometimes you need some dataset for your needs. For instance, for the demo that I showed you for drawing, and you need to create this dataset from scratch. So it's not available. You need to code it. Okay. Okay. Yeah. Yeah. No, so the question was, is it restricted for the local TensorFlow that you have? No. TensorFlow is a free library. The only thing that you need to train on something, you need to train models. So if you train in your own GPU, your own GPU might have only 2 GB of memory. So this Google Collaboratory allows you to train on 8 GB of memory for free. So you can train really large models for free. The question is whether we can connect Colab to other notebooks.
Yes, I mean, can you use Jupyter and connect it to a Google Cloud backend and use it for free to train?
I haven't tried this, but there is something here that's connect to local runtime, but I'm not sure how does it work. So you can connect to your local machine and run things directly from there. Yeah. Also, you can upload your a notebook to your drive, mount the drive, then run it there. Also, there are lots of cool stuff here. For instance, yeah, so if you have any, for instance, wait a little bit. So I have a couple of notebooks. For instance, this notebook, I can't change. And it will run directly on Collaboratory. You don't need to upload it actually. So this is a cool trick to convert anything from there. Yeah. Even on your phone, you can try the same demo on your phone. Yeah. Some browser might have like nobody uses Internet Explorer, for instance. Yeah. Yeah. And it's Internet Edge now, right? Yeah, they try to reduce the kind of bad stuff about it, so they change the name. Yeah. Okay. Okay. Yeah. You have a question, right? Yeah. Yeah, this is a good question. So about the performance for running in the browser. So running in your local machine is much better than running on the browser, because in the browser there is like a kind of a library that it's called WebGL that allows you to run stuff in the GPU. This library is really old, and this is the only library that's used for connecting to the local GPU that you have. So this makes things really slow, and your machine might just hang while you are running the model if it's really large. So it's better to use small models for some prototypes. You cannot run really large models there. So what I explained here is only for running on the front end for the for the people to try, for the users. There is another node that runs on the server, which is called Node.js. You can connect TensorFlow.js. I'm not sure about that. I'm not sure about the performance. Yeah. So we're done, right? Okay. Yeah. Yeah, so the question is the GUI will block while you are running them or trying to load the model. There are some ways around of this in TensorFlow.js, so I'm not sure about it. It's called tf.getNext something. It's there, but you can like continue running while you are loading the model, so you don't have to block the GUI. But I'm not an expert in this, so I didn't try it. Do you have any more questions? Okay.
Thank you very much, Zaid. This is really one of the best lectures. We're proud. It's all done by us, all of you guys. The one who come, the one who organized. Really special thanks to Asma. She's doing a lot of work for making those who cannot come today can watch it, because such a video, such a lecture should be put wherever for those who are really interested about learning about machine learning, and specifically TensorFlow. So please give a hard clap to Zaid, because you really done a very good job in explaining, and also we will share with you the video, the slides, and his GitHub. So really, if you want to go further into this area, and please give him a clap.